Instrumentation, Measurement, and Control, a tutorial. Integrated Philosophy for Instrument Selection and Process Control. Smart, auditable instrumentation decisions for maximum lifecycle efficiency. The selection of instruments must be executed through a collaborative effort between process technologists and instrumentation engineers, guided by total lifecycle value and operational suitability. Instrument selection is not a one-time task, but a systematic, auditable process that accounts for every credible operating case, from normal and alternate modes to startup, emergency, and commissioning events. To ensure relevance and reliability, selection involves thorough analysis of the process fluid, its phase, corrosiveness, fouling tendencies, etc., operating parameters, flow, pressure, temperature, environmental influences, accessibility, EMC compliance, maintenance burden, and authority-imposed safety or certification obligations. Beyond technical compatibility, project-specific vendor preferences, stock rationalization, and maintenance support must also weigh into the decision. The outcome must prioritize accuracy, total cost of ownership, TCOO, reliability, and compatibility with calibration or flushing systems. Standardized units for consistent engineering practices. All measurements and instrumentation must adhere to the International System of Units, SI, except in rare project-specific exceptions. This ensures universal interpretation, eliminates conversion errors, and streamlines communication across disciplines and vendors. Clear definitions for range, span, and adjustability. Understanding instrument configuration requires precise differentiation between range, device's full measurable capacity, span, difference between URV and LRV, and adjusted span, calibrated operating span. Design documentation must reflect instrument capability limits, URL-LRL, application-specific settings, URV-LRV, and validation that adjusted spans fall within the instrument's physical capability. Such clarity ensures calibration integrity and avoids operational misinterpretation. Strategic range selection, anchored in process accuracy. Range and accuracy must span the full operational window while maintaining measurement resolution, especially during abnormal operations. Design set points should fall within 50 to 75% of the selected range for highest fidelity. When abnormal modes make a single measurement infeasible, justified compromises or multiple devices may be warranted. All safety trip points must be set between 10 to 90% of range, avoiding elevated zeros unless process critical. Robust signal and power transmission protocols. Digital communication, especially HART over 4 to 20 milliamps, should be the preferred signal transmission standard between field devices and DCS, enabling diagnostics, configuration, and calibration. Field bus implementations must conform to recognized standards and only use proprietary protocols if fully evaluated under TCOO principles. Power sources must reflect instrument criticality, with UPS backing for high-priority applications and validation against UPS-induced transients. Explosion safety through classification-driven hardware selection. Instrumentation in hazardous zones must meet zone-specific protection standards. XIA is mandatory in Zone 0, while XD, EN, or other IEC-recognized types may be suitable in Zones 1 and 2 depending on national overrides. Full certification, e.g. CNLEC IEC-X, must accompany all devices, and field personnel must validate compatibility with site-specific area classifications. Field identification via durable, standardized nameplates. All plant instruments must be tagged with robust nameplates indicating tag numbers and service. Material selection, fastening method, preferably mechanical, and environmental compatibility must meet site-specific guidelines. For safety-rated devices, e.g. CL1 Plus IPFs, visual distinction is essential, e.g. red on black tags. Languages and naming conventions must reflect operator requirements and regulatory stipulations. Anchored to application class, the measurement accuracy of each device must match the process requirement class A through D. Custody transfer mandates high accuracy, e.g. 0.25% for liquid flow, while routine monitoring may tolerate broader error margins. Importantly, the system's presented accuracy must account for the full measurement chain, including density compensation, not just sensor specs. Material inspection, certification, and marking. Instruments are classified by exposure severity: inline, full process exposure; online, impulse tapped; and offline, isolated sensors. Each class has tailored requirements for material traceability, with the most stringent requirements applying to pressure-retaining components in sour or high-risk services. Only AISI 360L or appropriately certified alloys are permissible in most services, with documentation requirements aligned to pressure envelope design criteria. Visual functionality validation through lamp test facilities. All panel indicators and lamps must include a single operator accessible lamp test function with logic integration into the DCS or IPS to reduce manual error and support diagnostic procedures. Crippled mode detection to safeguard plant integrity. Instrumentation systems must discriminate between legitimate process excursions and instrument faults. Adherence to NAMR NE 43 standards ensures consistent behavior, e.g., using high-low clamp limits for process deviation versus failure signaling. Crippled mode strategies, controller freeze, alarm suppression, failure mode selection must be designed and implemented in tandem with device diagnostics and DCS capabilities. Environmental and EMC protection for harsh conditions. All field instruments must meet at least IP65 enclosure standards and IEC 60654 classifications for temperature, corrosion, and mechanical resilience. EMC compliance is mandatory and requires full metallic gland terminations, 360-degree bonding, and prohibition of plastic glands on signal lines. Smart signal transmission and resilient power infrastructure for field instrumentation. Signal transmission architecture must reinforce both operational reliability and lifecycle adaptability. Where analog outputs are employed, intelligent communication over the 4 to 20 milliamps loop should be the default configuration, enabling bidirectional device communication for diagnostics, calibration, and configuration. HART protocol is the industry-preferred standard supported across most vendors and providing backward compatibility with legacy analog systems. For digital integration, Modbus RTU is the preferred protocol between DCS and subsystems, e.g. analyzers, offering robust serial communication in master-slave configurations. Until fully standardized fieldbus architectures are universally adopted, project-specific proprietary digital protocols from approved DCS vendors are acceptable, provided TCOO evaluation supports the limited vendor flexibility they impose. Transmissions to final control elements from DCS must be standardized to 4 to 20 milliamps DC. In critical subsystems, e.g. machine monitoring, tank gauging, fire and gas detection, unique manufacturer-defined protocols are permissible when explicitly required by device function or industry standard. Pneumatic transmission, once prevalent in legacy systems, is now reserved for exceptional cases with principal approval. Where used, it must conform strictly to the 0.2 to 1.0 bar G signal standard and be justified based on environmental or safety rationale. Power supply design must reflect application criticality. Instruments serving safety, trip, or essential control functions must be powered from uninterruptible sources, 24-volt DC or 115-230 VAC, with operational stability guaranteed through full immunity to voltage dips, brownouts, or UPS switchover transients. All components must be verified to tolerate such events without signal loss or reset behavior. Lifecycle-oriented designs must also validate the compatibility of signal integrity, loop resistance, and powering current against remote mounting distances, Zener barriers, and input device load conditions, particularly in intrinsic safety loops. Power and signal planning must be integrated early in system architecture to avoid rework, miscommunication, or degraded diagnostic performance. Explosion-proof instrumentation design for hazardous area compliance. Electrical instrumentation must never pose an ignition source in explosive atmospheres. Design begins with area classification per IEC 6079-10, followed by protection strategy selection aligned to IEC 6079-114 and local regulatory overrides. Zone 0 demands the most stringent protection, XIA, intrinsic safety only, ensuring double fault tolerance and minimal energy conditions. Zone 1 allows options such as XD flameproof, AXIA, or XIB. In Zone 2, protection selection be risk justified and optimized for TCOO, with preferred methods including XN, XE, or XD, subject to system constraints and maintenance strategy. Certificate-backed compliance is mandatory. In Zones 0 and 1, all equipment must carry full type certification from accredited authorities, e.g. ATEX, IECX. For Zone 2, if protection is based on IEC standards, certificates are also required. If alternate standards, e.g., national codes or non-IEC industry specs, are applied, the design must still conform to the principles outlined in IEC 6079-14, clauses 5.2.3 and 5.4, including documentation of equivalent protection levels. Flameproof devices, XD, must consider enclosure strength, gas tightness of cable glands, and accessibility for maintenance. Intrinsically safe designs, AXIA, require holistic loop analysis, cable capacitance, inductance, energy limiting barriers, and fault tolerance validated at the system level. The design authority must assess local legislation and advise the principal where national codes override IEC standards. Under all scenarios, full safety documentation, certificates, control drawings, verification records must be available for inspection, project turnover, and ongoing compliance assurance. Strategic selection of protection type must balance equipment longevity, testability, certification upkeep, and site-specific maintenance capacity, ensuring protection strategies enhance safety without compromising accessibility, availability, or scalability. Performance-driven accuracy classes for fit-for-purpose measurement integrity. Measurement accuracy must align with the operational purpose of each instrument, not as a blanket specification, but as a calibrated response to process criticality, control dynamics, and consequence of error. Accuracy requirements are stratified into 4 tolerance classes, A through D, corresponding respectively to custody transfer, critical feed control, routine monitoring, and course supervision. Class A instruments support high-value or high-risk operations, demanding sub 0.25% accuracy for liquid flow, sub 0.5% for gas or steam, and sub 2 mm resolution for level. These are non-negotiable in fiscal transfer, reactor feed control, or emission monitoring. Class B supports process control with tolerances around 2 to 3%, while Class C and D allow for wider deviations in non-critical or trending applications. Accuracy expectations apply not to the sensor alone, but to the final presented value, especially in compensated measurements like mass flow or corrected level. A volumetric flow meter used for mass flow must include high-precision pressure, temperature, or density inputs to maintain total system accuracy within class boundaries. For example, a Class B liquid flow reading must reflect 2% error in its compensated output, not merely at the raw sensor level. Specifications must account for linearity, hysteresis, repeatability, and environmental effects, including static pressure and ambient temperature. These values must hold under all normal and alternative operating conditions. If accuracy degrades during startup, regeneration, or emergency shutdown, the deviation must be documented, justified, and approved by the principal. The pursuit of accuracy should not inflate cost or complexity without functional return. Instead, accuracy must be optimized, tight where needed, relaxed where permissible, always ensuring that the instrumentation system reflects a balanced, disciplined allocation of performance to priority. Mature material certification strategy aligned to pressure integrity and process exposure. Instrumentation must be categorized by its mechanical exposure to process conditions, inline, online, or offline, with material inspection and certification requirements tailored accordingly. This classification ensures safety, pressure integrity, and compatibility with piping codes, while avoiding over-specification that drives unnecessary cost. Inline instruments, such as Coriolis meters, turbine meters, displacer-level instruments, and control valves, are direct extensions of the process pressure boundary. As such, all pressure-retaining components, including bolting, must conform to the mechanical standards of the associated piping class or equipment code. Full traceability, material certificates, and pressure temperature compatibility are mandatory and enforceable under project mechanical discipline governance. Online instruments, including transmitters, pressure gauges, and analyzers connected via impulse lines, typically DN50, are indirectly exposed to process pressure. Where proper block valves isolate these devices, material certification may be waived, except in the following high-risk cases: all impulse tubing, regardless of service, any wetted component in sour or wet H2S service, which must comply with ISO 15156, NACE MRO 175, production facilities, or NACE MRO 103, refining and chemical plants. Certification must cover pressure exposed to corrosion states under all conditions. Offline instruments, such as thermowells, signal converters, and local indicators, are not in contact with process media and thus require no material certification unless otherwise specified. Material selection must not only meet mechanical integrity criteria but also reflect corrosion resistance and long-term process compatibility. For example, in sour service, standard stainless steel components must be verified for resistance to sulfide stress cracking. For hydrogen fluoride HF applications, wetted components must be Hastelloy C276 in strong reducing acids, e.g., pure HCl, H2SO4, Hastelloy B2, and tantalum diaphragms are mandated. All such choices must be visibly marked and traceable to avoid installation error. Certifications must be retained for audit, commissioning, and regulatory inspection, forming a critical part of the instrument data pack. The certification regime must not be treated as an afterthought, but as an integral component of the design integrity envelope. Crippled mode detection and strategic signal shedding for fault-tolerant measurement loops. Modern analog transmitters must not only measure, they must also self-diagnose and differentiate between legitimate process extremes and genuine system failures. Crippled mode detection is the engineered response to abnormal conditions such as sensor drift, line breaks, short circuits, or internal electronics failure, enabling the control system to maintain safe and predictable behavior under degraded signal conditions. Transmitters operating in 420 mA analog mode must incorporate signal clamping features. When the measured value falls outside the calibrated span, the output is held at a defined low, e.g. 3.8 mA, or high, e-high, 20.5 mA clamp limit. This prevents nuisance alarms during normal process underrange or overrange excursions. True failures, such as internal fault, power loss, or cable damage, must push the signal beyond the clamp thresholds, triggering a diagnostic alarm in the receiving system, DCS or IPS. To enforce uniform behavior across diverse equipment, transmitters should comply with NEMR NE 43, which defines signal ranges: 3.6 to 3.8 milliamps and 20.5 to 22 milliamps for fault indication, Strat 3.8 to 4 milliamps and 20 to 20.5 milliamps for process underrange, overrange, 4 to 20 milliamps as the normal measurement range. Upon detection of a crippled signal, the control system must execute a predefined shedding strategy, not just generate an alarm. Strategies include freezing PID controller outputs at last known good value, switching control loops to manual mode, suppressing associated process alarms, automatically switching to redundant measurement if available. These actions prevent cascade faults and allow the process to degrade safely until corrective action is taken. The design team must assess crippled mode compatibility between transmitters and receivers. Differences in vendor implementations may require adjustments in software, signal conditioning, or hardware thresholds. For example, loop-powered transmitters with long cable runs may fail to exceed the NAMR-defined high current limit in a short-circuit scenario. Similarly, Zener barriers may restrict current flow, masking failure detection. Shedding logic must be embedded in the control narrative from the earliest project phase, and diagnostic functions must be thoroughly tested during FAT-SAT. Where loop diagnostics are mission critical, digital protocols, e.g., heart diagnostics or field bus status flags, may supplement or replace analog current signaling altogether. Crippled mode design is not optional. It is a minimum standard for intelligent control and is essential to meet safety, reliability, and operational continuity expectations in modern instrumentation systems. Environmental hardening for instrument survivability in harsh operating conditions. Instrumentation must be engineered not just for measurement precision, but for enduring environmental resilience across a facility's full climatic and physical spectrum. Design specifications must ensure instruments function reliably in industrial, humid, saline, and corrosive atmospheres without degradation, drift, or premature failure. All field-mounted instruments must meet or exceed IP65 enclosure protection, IEC 60529, providing full protection against dust ingress and water jets. For outdoor environments, instruments must comply with IEC 60654-1, location class D2, accounting for wide ambient temperature ranges, solar radiation, and condensation cycles. Mechanical resilience must conform to IEC 60654-3, ensuring devices withstand vibration, shock, and structural stress without operational compromise. For corrosive exposure, compliance with IEC 6CCL 654-4 Class 1 or 2 stress is required, depending on whether the ambient air is classified as industrial clean or moderately contaminated. Class selection must be confirmed in the project environmental specification. In tropical zones, where condensation, high humidity, and biological contaminants, e.g., insects, nesting animals, are prevalent, special measures are required. These include antifungal coatings on PCBs, UV stable housings, sealed gaskets resistant to temperature cycling, insect screens over ventilation paths and gland entries. Instrumentation deployed in marine terminals, coastal plants, or offshore platforms must include hermetically sealed housings to block salt-laden air intrusion, marine-grade materials and anti-corrosion surface treatments. Consideration of splash zones and pressure washing during maintenance. Where SASH, H2S, SO2, or other corrosive vapors exist in trace quantities, common near sulfur units, acid plants, or combustion zones, relay and switch contacts must be gold-plated 10 mm or enclosed in sealed housings to prevent oxidation-induced failure. These trace gases may also accelerate corrosion of exposed electronics and must be mitigated by appropriate housing material and sealing class. Environmental specification must be a front-end input into vendor selection and design approval. Instruments not adequately protected at the design stage will become chronic maintenance liabilities. All environmental controls, sealing, coating, mounting orientation, shielding, must be confirmed by engineering review and explicitly reflected in datasheets and inspection protocols.